Let me just pull up the PowerPoint. All right. So what we were talking about on Monday is that we were looking at everything we learned about quantum mechanics and electron orbitals and how to place electrons in these orbitals. And then we were using that information to describe why elements behave the way they do. So we looked at orbitals and their desire to want to get to a full octet. And that's why our halogens are -1 because they're 1 electron away from a full octet. And that's why our group 1 metals are +1 because when they lose an electron, they get their full octet, just like our noble gases in group 8A, right? And so we looked at how to write electron configuration for ions. And then we looked at magnetism. So remember, if you have an unpaired electron in your orbital diagram, you're paramagnetic, while if all of the electrons are paired up, you're diamagnetic. And so we looked at that. Then the last thing we looked at was size of atoms. So the way to use your periodic table for size is that as you go down the periodic table and you go to the left, the size of uncharged atoms will increase. Remember, so this trend is for uncharged atoms only. So no ions, but neutral atoms, when you go down the periodic table and you go to the left, these atoms will get bigger. And then we looked at a problem where we needed to pick the largest atoms. Now, what we're going to look at is how atoms and ions, how their sizes can change. So first, we're going to look at cations. Remember, a cation is positive or positive. And what happens for a cation is that you are taking electrons out of the shell that is furthest away from the nucleus. And generally, you will take all the electrons out of that shell until you are like a noble gas. Now, what happens when you take electrons away? One, you are just shrinking the size because you're removing them from the outer shell. But also what happens is that you're taking away negative charge, right? Remember, electrons are negative and protons are positive. So we're taking away negative charge. That means any electrons that are still left in the atom get sucked in closer to the nucleus because they have less competition to be with the nucleus, right? And what that means for us is that when we compare a neutral atom to a charged atom, the neutral atom is bigger. So a positively charged or a cation shrinks because their electrons are being pulled in. And just a reminder, remember that when we look at an atom, the nucleus is super tiny. Most of the atom is made out of empty space. And these shells that we're seeing, you can think of these as electron clouds, right? They're just this area where electrons can be found, right? And as we remove electrons, that cloud will shrink as electrons are being sucked in and we are physically removing them. So cations, we shrink. The bigger the charge, the more we shrink by. So a +2 ion shrinks more than a +1 ion. A +3 ion shrinks more than a +2 ion. So that's cation trends. Anions do the opposite. When we add new electrons, remember, anion, you can think of it as a negative ion. So anions, we are adding electrons to our atom. When we're adding electrons, we're adding more negative charge. So the electrons are going to want to repel even more because we're adding that more negative charge. And remember, I said this shell is like an electron cloud. So you're having repulsion. This cloud is growing, and in essence, our atom is growing when we become an anion, and it's the same idea here, where like the more negative charge you have, the bigger your atom becomes. So a -2 charge is bigger than a -1 charge, as being shown here. So your takeaway is cation, your atom gets smaller. Anion, your atom gets bigger. So any questions about those ideas? If not, we will get to some problems where you can test those ideas and just make sure that we have them. All right, so here are some simple questions. I just want you to pick what the larger atom is in each case. And then for our last question, you need to order the atoms from small to large. And I have a poll here, so you can answer A, B, C, D, and E. So let's see if you can decide which atom is largest in each pair. So do another about 30 to 40 seconds if you haven't got your answer in yet. All right, so let's take a look at these. It seems there is some confusion as just about every question is about 50-50 split. So the rules really aren't that difficult. So if you're a cation, whoops, I need to get my pen back out. If you're a cation, remember, cation means positive charge. You shrink, right? If you're an anion, which is a negative charge, you grow. So what's the larger species? Lithium is bigger than lithium plus because as you become a plus, you shrink. I minus is bigger than CS plus because as you become negative, you grow. And if you look on the periodic table, right, CS plus and I minus have the same electron configuration, right? They both have the electron configuration of Xeon. And so when you are comparing isoelectric series, and that's what this is, these two are actually electronic, which means you have the same electron configuration. The negative is always going to be bigger because of what we talked about. As you add more electrons, your electron cloud grows because it repels. So CR is bigger than CR3 plus. O2 minus is bigger than O. N3 minus is bigger than N. And if we arrange these from small to big, you go from the most positive to the most negative. So that's small to big. All right, now that you've seen that, questions about that? Right? And if there's no questions, or if you're typing it out, that should be our last, yeah, that's our last slide for this PowerPoint. So what I'll do now is I'll switch to today's PowerPoint. So question is, so with ions, you look at charge instead of table the majority of the time. You do have to look at the table. For example, if I said what is bigger, let's see, what do I want to do? If I said what's bigger, BR minus versus O2 minus, BR is bigger because it's further down on the table. And so that's going to trump the difference in two charges. But I probably will not give you something like that. In all of the examples we did, right? N versus N3 minus, you're looking at the same atom, just with a different charge. So there, as you add more and more electrons to the same atom, that atom grows. When we're looking at CS plus versus I minus, those are isoelectronic. They both have the same electron configuration that Xeon does. So there again, the table really doesn't matter when you're talking about isoelectronic species. The periodic table can matter for the reason I said right here, but right now, not too concerned about doing something as complicated as that. I just want to know if we have the bare essential, do I know the basic rules down? How can I tell which is larger, some anion or positive from row 3 or something from 4? I'm not quite sure I get that question. But if you're saying like, if I have, if you're saying if you have something from the 3rd row versus something from the 4th row, and like one's a minus and one's a positive, how do I like figure that out? So there, you can get in some tricky situations, but basically if they have the same electron configuration, so if same electron configuration, the negative is always the biggest. If it's something more complicated, like let's take a look at RB plus versus let's do O2 minus again. There, RB plus is bigger because it has more electron shells, right? So generally, the thing with more electron shells is going to be bigger, even if it's positively charged. That's not always the case. There are some discrepancies for that. We can't go hard and fast rules, but in general, the more electron shells you have, you are generally bigger, but not always. That is why we just learn about trends. And remember, the trend is for neutral atoms, as you go down and as you go left, you get bigger. For when you become a positive ion, you shrink, or cation, and when you become an anion, you grow. These pieces of information, that's what we need to know. And these questions that I would ask you on the test, they're going to be no more complicated than what we saw today or previously on the lecture. All right. So if you have other questions, feel free to ask them. Otherwise, we will move on. Not a lot of new information today. So those of you who are hoping that test 4 can be a good test for you, it is going to be the shortest amount of information we have on the test or on all the 4 tests. So it is a good opportunity to make up that grade. Anyways, what we're going to talk about is ionization energy. Ionization energy is the amount of energy needed to remove an electron. And the way these are measured are in the gas state. So you take an element, you make it a gas, and you measure how much energy it takes to remove an electron. This is endothermic in that you have to put energy in to remove an electron, which makes sense, right? So put energy in. And I say that makes sense because remember, the nucleus has protons in it. The electrons are negatively charged. These things want to come together. And what you're doing is physically pulling away an electron. It's like separating 2 magnets, right? You need to put in energy to separate 2 magnets because they naturally want to come together. And valence electrons, and remember, valence electrons are those electrons in the outer shell. Those are easiest to remove, and they have the lowest ionization energy. And you can have multiple ionization events. So here, this M just stands for a metal. That's not actually an element, it's just metal. So to remove an electron from the metal, I have to put in enough energy. So IE1, IE1 stands for ionization energy 1, or the first ionization energy. And that is how much energy it takes to remove your first electron. So when I put in that energy, I get a positively charged metal and 1 electron. And you can keep doing this until you run out of electrons, right? So my metal, which is now +1, if I put in enough energy to remove the second electron, i.e. 2, I become metal 2+ and 1 electron. And as you remove electrons, ionization energy goes up. So the second ionization energy is greater than the first, and the third is greater than the second, and so on and so forth. And the idea of that is when you remove electrons, you're becoming positively charged, right? And so, like we said, you're shrinking. And you're shrinking because your electrons are more and more attracted to the nucleus. And so if I remove this electron, all my other electrons are going to move closer because they feel the nucleus more. So it's going to take more energy to remove those electrons from the nucleus. And we do have trends in the first ionization energy. That is, how much energy does it take to remove the first electron? And these trends are more or less the trend of the periodic table is basically the same as the trend for a size, in that as you go down the periodic table, the first ionization energy decreases. As you go from right to left on the periodic table, the first ionization energy decreases. There are some exceptions to this, one being nitrogen. So nitrogen has a higher ionization energy than oxygen, for example. But in general, as you go down the periodic table, ionization energy decreases. As you move to the left of the periodic table, ionization energy decreases. That is, it's easier to remove electrons. That's what decreasing ionization energy means. Easier to remove electrons. Any questions so far about those ideas? All right. So what I want you to do is take a couple minutes with your periodic table. And for 1A, just tell me from low to high what the first ionization energy will be. And for 1B, from high to low, what is the order of the first ionization energy? So take a few minutes to see if you can figure that out using your periodic table. So remember, when we're looking at the trends here, just rewrite it. As we go down the periodic table, it decreases. As we go to the left, it also decreases. So a lot of this is a game of find the element. So if we look at these four, the furthest down into the left is In, followed by silicon, followed by nitrogen, and then followed by fluorine. In, Si, N, and F. And then B, we can play that same game. So the furthest down into the left is lead, followed by tin, then sulfur, and chlorine. Oh, I wrote that backwards. I'm sorry. This is supposed to be decreasing. Chlorine, sulfur, tin, lead. So chlorine's your highest. Lead is your lowest. Tin, not SN, not SB. I cannot write anymore. So it should be chlorine, sulfur, tin, lead. Yeah, PP. There we go. Lead. So chlorine, sulfur, tin, lead. And then here I'm going from low to high. So size doesn't matter in ionization energy. It does, right? Kind of. Here, if we look at lead, lead is our biggest element, biggest neutral element. It also has the lowest ionization energy. So I can also put the sizes there, right? This is the biggest element. This is the smallest. This is the smallest of these four. This is the biggest. So there, and these are all neutral, by the way. So there is some correlation to size. It's just kind of reversed. Something that's big, it's easy to remove an electron. And again, that makes a lot of sense. If I'm an atom and I'm big, that means I have electrons like far away from me. So it's easy to remove that electron. So let's say this was lead compared to something like chlorine, which is smaller. Well, since I'm closer to the nucleus, because of Coulomb's law, remember Coulomb's law, and this is combining multiple things we've learned. Coulomb's law is charge of atom or particle 1 multiplied by charge of particle 2 divided by distance, right? And so the closer I am, the more favorable energy or interaction I have. So the smaller I am, the closer my electrons are to the nucleus. Therefore, it is harder to remove those electrons. High ionization energy. While if I'm big, my electrons are far away from me. Since they are far away from me, they don't have that much interaction with the nucleus. So it's easy to remove those electrons, therefore low ionization energy. Is N smaller than F? No, N is not smaller than F if you're talking about a neutral element. F is smaller than N. And we're talking about neutral elements here. If we were talking about non-neutral elements, then things would be different. But here we're just talking about neutral elements. Any other questions about this? All right. So let's take a look at what happens as you remove more and more ionization energies. Like I said previously, the first ionization energy is always the easiest. It takes more energy to remove the second and the third. And for valence electrons, this is a like regular increase, right? So let's look at aluminum. Aluminum has 3 valence electrons. So removing the first is 578 kilojoules per mole. The next one is 1800. So this is like an increase of like 1300 kilojoules. Oops, 1300 kilojoules. Going for the second to third, this is an increase of like 900 kilojoules. Nothing, I mean, fairly regular. Sure, you're off by 400, but you're in the ballpark. Now, look at what happens when you go from ionization energy 3 to 4. This is a difference of roughly 9,000 kilojoules. So a different magnitude. And that's because removing valence electrons is relatively easy. Removing core electrons takes a lot of energy. And so you'll see that when you're looking at successive ionization energies, once you hit the core electrons, it takes a lot more energy to remove those than it takes to remove the valence electrons. And that's what that chart is showing you down there. So what I want you to tell me is I want you to tell me where that big energy jump happens for each of these elements, right? And the easiest way to do this is to write down the electron configuration. So I'm going to do that for beryllium. Beryllium has the electron configuration of 1s2, 2s2, right? And so it has 2 valence electrons. Therefore, the big energy jump happens at ionization energy 3, because ionization energy 1 and ionization energy 2 are removing valence electrons. So the energy needed to remove those are going to be much, much smaller than ionization energy 3, which is a core electron. So where I'm saying jump, what I mean by that is where does the energy increase a lot, or what ionization energy are you starting to remove core electrons? You can think about it either way. So I'm going to give people just a minute or two, a couple minutes to see if you can tell me what ionization energy what ionization energy does the jump occur at for each of those atoms shown? So question, why is it IE3 and not IE2 if it's the valence electrons? Because IE3 is when I take away a core electron. Ionization energy 1, so IE1, is I remove 1 core or 1 valence electron. And so the energy for that is relatively low. Ionization energy 2 is when I remove the second valence electron. So again, the energy is still relatively low for that. Ionization energy 3 is I have just removed a core electron. Atoms do not want to lose their core electrons at all. And so that's where a giant energy spike will happen, where you need to put in a lot more energy to remove a core electron than you do a valence electron. So that's why it's IE3 and not IE2. IE2 is still a valence electron. Let's take a look at nitrogen. Again, I'm going to just write down the electron configuration because it makes it way easier for me. Electron configuration of nitrogen is 1s2, 2s2, 2p3. So this has 5 valence electrons. Therefore, the ionization energy or the big jump happens is IE6, right? Because the first 5 ionization energies, 1, 2, 3, 4, 5, I'm removing valence electrons. However, at the 6th ionization energy, I start to remove a core electron, which takes a lot of energy. So that's where my energy jump is going to happen. Oxygen, 1s2, 2s2, 2p4. So therefore, it's going to be IE7 because I have 6 valence electrons. So the 7th, I'm going to remove a core electron. And hopefully you're seeing the pattern here now. Lithium is 1s2, 2s2, 2p6, 3s1 has 1 valence electron. So the big jump is going to happen at IE2 because the second time I try to remove an electron or the second ionization energy, it's going to take a lot of energy to do that because it is a core electron. So to figure out the jump, to figure out what this number is, it's the number of valence electrons plus 1. That's all it is, right? So beryllium, Be had 2 valence electrons, so it's IE3. Nitrogen, 5 valence electrons, IE6. Oxygen, 6 valence electrons, IE7. Lithium, 1 valence electron, IE2. All right. Any questions about ionization energy or where to predict a jump at, the jump of ionization energy or a large increase of ionization energy? Right. If not, that I believe, yeah, that's all I have for you today. So we can end a little early, and we'll probably end a little early on Friday too. Don't have much to cover on that front as well. So again, hopefully test 4, like I said, if you haven't been doing so well on the test 4 is definitely your opportunity to make it up because it's going to have the least amount of info on it. If you have any questions about anything at all, as always, feel free to email me. I'll put a homework up that just reinforces what we went over today. And I will see people on Friday. Take care, everybody.